now whatever we seen, this is the basic for the feature extraction engine, or the Mel filter receptor coefficients. So from this, what if you want to develop any hardware or any system, we need to analyze the input signals, and we need to understand and the mathematical functionalities. These functionalities, when we convert into a hardware, or when we try to implement as a system, we need to analyze and we need to understand more features from the inputs. So what is the input we have is exactly the speech signal. So human can easily understand the speech, but when the machine want to understand the speech, it need a frequency component or else a spatial component, because the time domain signal in the direct wave, the system or the machine can't able to understand easily. So if it want to understand a machine readable information, we need to extract the features. So to extract the features, we need a spatial or a frequency domain. So to convert the domains, we are going to use the FFT, so fast Fourier transform. So after this, the feature analysis is done with the Mel spectrum with the Mel filter bank. So the signal energy is computed with the correlation between the Mel bank and the FFT magnitude. This will be explained in the later, how we are going to correlate the Mel bank coefficients with the FFT magnitude. So whenever we are correlating the FFT magnitude with the Mel bank, we are trying to extract the exact frequency component or the exact feature component from the Mel bank. So the next step, we are trying to calculate the log and the cost computations. So this log of cost or log multiplication with the cost actually trying to extract the linear portion of a nonlinear vector from the speech signal. So whenever we speak something, actually it's a perfect nonlinear signal. So this nonlinear signal, when we convert it into a frequency domain, we'll get the linear frequency components, or else what are the frequency components are there, we can able to extract it. These frequency components, we are trying to get as an energy spectrum. Using this energy spectrum, we are trying to map with the Mel bank, and the Mel bank frequencies are extracted. This Mel bank frequencies are imposed with the log computation. So again, the log actually will do the linear to nonlinear conversion or nonlinear to linear conversion. So this linear extraction of a energy vector will be done with the log computation. But normally, whenever we trying to extract any features, the spectrum has to do with the inverse transform. So this log of a signal energy has to done with the inverse transform. To do this inverse transform, we are going for the cosine transformation function. This cosine transformation function will be done with the cost multiplication along with the summation. At last, after done all this mathematical functionality, we'll get the output as a feature vector. So once again, we'll refresh what are the specifications for our system. So we need, in case if you want to develop any hardware or any system, we need actually a basic input parameters, or at least a basic initial conditions. So whenever I said the analog to digital conversion, that means the speech signal is a direct analog signal. So whenever we trying to convert into a digital domain or digital signal, we need to sample it. Also, we need to convert into a digital signal. So this first rate as a sampling rate, the sampling rate will be fixed with the 8 kilohertz and the 16 kilohertz. It means per second we are going to sample 8,000 samples or else 16,000 samples. So after a sample, we need to convert the samples into a digital signal. So the ADC, which that means we are considered the ADC output will be 16-bit accuracy. It means each and every sample is 16-bit length the binary. Then the input frequency means the voice frequency whichever we are receiving, it's from 300 Hz to 3.3 kilohertz, which is actually the voice spectrum range. So next, the frame period means whenever the speech signal is extracted and whenever it is sampled, later we need to process the sample. For processing the sample, we need a frames of signal. Means we can't process the entire signal since it has an infinite range. So we need a finite range of samples to process and to extract a basic features from within the frame. That means the frame period what we are going to fix is 25 milliseconds, which is a minimal and optimal range. And if it is a 25 millisecond in the sense, per second we have 8,000 samples, so per frame minimum we have 200 samples. But this frame has an overlap between the first frame and the next frame. It means the overlap period is fixed for the 15 millisecond. It means per frame for the 15 millisecond we have 120 samples. This 120 sample is correlated or it's overlapped between the frames. So per frame 80 samples is the non-overlap samples. Then the samples per frame is a 200, and then FFT size. Whenever we are going for the FFT, it should be there in the 2 power n. So after 200 or 400, that means 8 kilohertz and 16 kilohertz samples, the near 2 power n value will be 256 or else the 512 respectively. So for the 8 kilohertz, we need to do the 256 point FFT, and for the 16 kilohertz, we need to do the 512 point FFT. But the major constraint here is whatever the sample we received as a frame, which will have only 200 samples, it not has a 256. For the remaining 56 or else for the remaining 112, for the 8K and the 16 kilohertz, we need to pad the zeros. This zero padding should happen within the clock cycle of the sampling frequency or else the framing frequency. So when, as I said, the frames has an overlap, so 80 clock cycle is a non-overlap period. It means at whenever the sampling starts at 0th clock to 200, that means 199, we'll get the first frame. But the second frame will start at 80th sample to the next 200 sample. It means each and every frame has only 80 clock cycle independently. The remaining 120 clock cycle is an overlap. So after the first frame, each and every 80 clock cycle, we'll get the consecutive frames. It means the system has to build within this 80 clock cycle time period so that it will be suitable for the real-time application. Or else we need to increase the operating frequency, or else we need to have the extra control logic to map or to make this features with the same timeline. So the FFT size is the first drawback or else the critical point to design the system. The second one is a MEL filters. So the MEL filters is nothing. It has a series of banks or the banks of frequencies. These banks of frequencies are defined with different frequency range from the voice signal of 300 Hz to 3.3 kilohertz. So this bands of frequencies will be divided with different range based on the sampling frequency. In case if I use a 8 kilohertz sampling frequency, my MEL filter coefficients will be different. If it is 16 kilohertz, the coefficients will be different. So as we see in the previous slides, the formula or the MEL bank energy spectrums will be computed and it will be stored in the VRAM because it's a one-time calculation. We don't need to keep a extra additional hardware. This MEL filter coefficients are computed based on the sampling frequency along with the number of filter banks. So 20 will be the optimal range. Normally it has a 20 to 40 filter bank, but 20 will be the optimal range for 8K and 16K sampling frequency. And the next one is a cepstral coefficient. How many cepstral coefficients or how many cepstra we need or we need to extract from each frame is defined with 12 cepstral per frame. So this 12 also a optimal MFCC order range. So more than 12 it will be better. So the minimum range will be 12. And the MFCC order is fixed with the 12. The next one is a non-linear, non-zero coefficients of the MEL bank. It means the MEL bank, whenever we computed, it has a non-zero coefficient, also the zero coefficient. Each and every bank has a minimal number of non-zero elements. The remaining coefficients, everything is zero. So whenever we try to multiply this 0 with another element, we'll get the result as 0 again. So instead of storing this redundant zeros again and again, we are trying to store only the non-zero coefficients. For the 8 kilohertz, we have only 240 non-zero coefficients, and for the 16 kilohertz, it's 477. And for the number of clock cycle per frame is 80 and 160. The reason it is has a non-overlap period. It means after the first frame, the next consecutive frame will be obtained with the 80 clock cycle for the 8 kilohertz and 160 clock cycle for the 16 kilohertz. So based on all these observations, we are trying to build the basic version of the speech recognition, MFCC. So this MFCC, the basic version, doesn't has the FFT version. So after the FFT means after the domain conversion, the energy computation and the central computation is done with the basic version 1 architecture. So for doing this basic architecture, first we need to analyze, or we need to understand the mathematical functionality behind it. So first we need to compute the S of n. The S of n is the energy spectrum. To compute this energy spectrum, actually we need two things. One is the FFT magnitude, the other one is the MEL coefficient. After the FFT, that means whatever the computation we are doing, the FFT, after the FFT we will get n by 2 unique coefficients, because once we do any transformation functions, we will get the mirror image or the mirror frequencies, which we no need to compute again.